So now we will move to the next chapter. So what's this Poisson paradigm? What is Poisson? So let's say x is a discrete random variable. And if it can have a value 0, 1, 2, 3, 4, the probability that it has value k is mu to the k times e to the negative mu over k factorial. Then we say that this is a Poisson distribution with the mean mu. So this is expectation mu. So why is it important? There are several reasons why it is important, but for our case, if we have n events and it's with probability p, then let mu be np, which is the expected number of events happening. So we want to count the events which happened, and those events happened with probability p. Assume they are mutually independent. Then what's the probability that, so x is the number of events happen. Then the probability of getting x equal k is n choose k times p to the k times 1 minus p to the n minus k. And we make n large and p small. Then we can actually show that this limit actually goes to, so just taking n large and then p small so that the mu is some fixed number, and we can actually show that this converges to this Poisson distribution. So if there are many rare events and we want to somehow compute the probability that k of them happen, then we can approximate this by the Poisson distribution. But this is under the condition that those events are independent. Then what about the events are not necessarily all independent, but the dependence between them are somewhat weak? Then can we still somehow approximate those by using this Poisson distribution? That's what we are gonna deal with in this chapter. So we have some events which are loosely dependent, and we want to approximate them by Poisson distribution. So, for example, consider G and P, and we want to the probability this is triangle free. To make the situation simple, it's let's say P is some constant times C. If this is 0, 1 over n, or this is P O 1 over n, then we can actually check that in this case it is almost surely triangle free, and in this case it is almost surely not triangle free. So for the some non-trivial case, we can consider this. And expected number of, say, x is triangle. Expected number of triangle is n choose 3 times p cube. And there are n choose 3 distinct sets of size 3, vertex sets of size 3, which can possibly form a triangle. And let's say S is a vertex set of size 3, and ES is the event that S forms a triangle. Then probability of this ES is 1 minus p to the cube. Then, what about for two different S and S prime? So what's the probability that both of them happen? Give me a moment. Why did I write? Okay, increasing. So then this probability, it's easy to check that we have this inequality, because if S and S prime, if they share at most one vertices, then they are independent. This form triangle, this forms triangle are independent. If not, then these, if they share two edges, two vertices, then one edge, one pair, then probability that both of them happen is p to the 5, while this is p to the 3 and p to the 3. So meaning that these are increasing probability. Increasing event. So from this, what we can prove is that the probability and GMP is triangle free is same as probability that the number of triangle is 0 is at least 1 minus p to the 3 to the n to 3. So you consider all n to 3 events and you multiply the probability, then that provides a lower bound. And this is roughly e to the negative n to 3 p cube, which is e to the expectation. So let's write mu as an expectation. And this is when you plug k to the k equals 0 here, right? So where were I? So we have this lower bound. But how good is this lower bound? Somehow this dependency between these events are weak, in the sense that there are n to 3 such events, and once a given event is given, S is given, in order to, the dependent events are the ones that share two vertices, so there are only n of them which is dependent to this ES, and rest of them are not. So by using that, we want to also prove our upper bound. So you might think that you might see that this situation is somewhat similar to the situation that we were dealt with in the local lemma. In the local lemma, there are many bad events, and we wanted to show that none of them happens with a positive probability. But here, we want to actually find the probability that none of the bad events happen. Give me a moment. I think here I said something not correct. Give me a moment. This is not the case. This is not the case. Then yeah, so sorry. So we actually have to take the, the event that this is not a triangle. Yeah. You can actually check that this also holds. Because the probability of not happening and not happening is same as S prime is 1 minus probability of both of them happen. And this is probability of one happen, the other happen, plus probability that both of them happen. So this part, so you want to compare this with 1 minus probability of ES and 1 minus probability of ES prime. So this is the right hand part. This is again 1 minus probability of ES minus probability of ES prime plus probability of ES and probability of ES prime. So if we know inequality, if we know this inequality, then it follows that these two, we can also compute these two, and this inequality holds. So we have this. Anyway, so now we want to consider upper bound. So we consider the following general setup. Let omega be the finite universal set. And for each r inside of this omega, we independently add r to this set R with certain probability which depends on R. Then R is a random subset of omega. And let I be an index set. And for each I inside of I, inside of capital I, let AI be a subset of this omega, and PI be the event that AI is subset of R. Again, it's similar to what we have done before. So each of these R is gonna be pairs in the random graph, and these R forms the collection of edges in the random graph, and this is the event. So AI is a triangle, and this is the event that we get a triangle in our random graph. And let xi be indicate a random variable. If pi happens, this is 1. Otherwise, this is 0. And let x be the summation of xi. So it counts the events that happens. So none of the events happen is same as x equals 0. And we write that if I and j are in capital I, we write they are related if pi and pj are not pairwise independent. Which can only happen when AI and AJ contain some element. Because all the elements are independently at random added to R. Then what do we know is PI is mutually independent to all the events Pj where I is not related to J. And with this setup, let delta be the ones which measures the dependency. So for all dependent events, we add a joint probability. So of course all the events are independent, then this is 0. And if this is high, that means there are strong dependency. If this is small, then dependencies are weak. And let m be the lower bound we get. So assuming all the things are independent, then this is what we get. And this is sum of ordered pair. So delta is sum of ordered pair, and delta over 2 is sum of unordered pair. Yeah. So I have to add that for ij different, we define this. We write mu for the expectation of x. Then what we want to show is this Jensen's inequality, Jensen inequality, which provides an upper bound. In the above setup, if we know that the probability of bi is m-os epsilon for all I, so events are somewhat random, then what we have is we have that the probability of none of the bad events happen is lower bounded by m and upper bounded by m times delta over 2 times 1 minus epsilon. And also upper bound can be obtained by e to the mu plus delta over 2. So if delta is small, then this is close to 1, and this is small, and m is approximately e to the negative mu. So this provides almost matching upper bound from the lower bound. So as long as this delta is small, this provides a good upper bound. And before moving to the next video, let's define one thing. If we have an event, we say this is an increasing event or decreasing event. If R satisfied and if R prime is superset or R prime is subset, then R prime also satisfies this. So in the first case, you say that this is increasing event, and second case, this is decreasing event. So why do we define this is that later we will mention slight generalization of this Jensen's inequality. This Jensen's inequality is about this specific setup. So we have these elements and which belong to R with a specific probability. Those are independent event. So this setup are built on these mutually independent events. But actually later we will talk about slight generalization that's not really necessary. Anyway, with this setup, what this Jensen's inequality says is that as long as this delta, which measures the dependency, are small, then we can find the almost matching upper bound. In the next video, we will prove this.